Yeah.
Yeah, okay, it started recording. So, good evening, everyone, and welcome to the second talk of our Astro Week. So, today we are honored to have Professor Sanjit Mitra from IUCAA with us to talk about gravitational waves. So, Dr. Mitra works on the detection of the stochastic gravitational wave background and has also worked on the CMB experiments. He is a part of the LIGO-Virgo Scientific Collaboration and the IndIGO consortium, and also the Planck Collaboration, which worked on the CMB. Sir obtained his PhD from IUCAA in 2006, and after that he did postdocs at the Observatory in Paris, in France, and JPL Caltech, and was a Planck scientist at the UC Santa Barbara. He has received numerous awards, including he was a co-recipient of the Special Breakthrough Prize in Fundamental Physics in 2016 and the Gruber Cosmology Prize in 2016 for the detection of gravitational waves. He was also a co-recipient of the Gruber Cosmology Prize in 2018 as a part of the Planck team, which detected the CMB temperature and polarization anisotropies. He has won numerous other awards, including the Swarna Jayanti Fellowship. So with this short introduction, I'll invite Sir to talk about the eventful beginning and future of gravitational wave astronomy.
Very good evening, everyone. Hope you can hear me.
Yes, we can hear
you. Yeah, and you can see the slides also as okay.
Yes.
Right? Yeah. Okay. So this is going to be a very brief introduction to gravitational wave astronomy. It is going to take. How much time do I have?
We have enough time. We have 1 hour at least.
1 hour at least. Okay. So it may take 1 hour, but even then we will just
we can go beyond.
Okay. So we will just sort of touch some of these aspects which may be of interest to you. So I think if you have a question, you should just try to interrupt and get it cleared, because there is no way you can learn everything, and a lot of material which I'm going to cover is anyway available on the internet. You just have to search it properly. So I think the idea would be to get something cleared out rather than understanding everything. Okay, so here we go. So it is okay. The title was the eventful beginning, and which is also a grand beginning. But eventful has sort of two meaning in gravitational waves. As you know, the sources which we have been detecting so far, that is the merger of compact binaries, which I'll tell you shortly about. They are not persistent on the sky. They come and they are there just for less than a second most of the time. So it is like an event, and so that's why it is eventful beginning and future prospects. Okay, so first, that this, I think most people are listening to this talk because of this event, which happened in 2015, that two LIGO observatories detected a signal when two black holes inspiraled, then touched each other and merged and formed another bigger black hole, which emitted a ring down signal, and then meaning it damped and then became a stable black hole. And this is the signal. This red and blue are the signals which were received in two different detectors 3,000 kilometers away. And since this has a very specific characteristic, frequency and phase evolution, which we will talk about a little later, and these two came almost at the same time, within milliseconds difference, depending on where on the sky the event took place. And since we could rule out that there was no other artifact which could affect the detectors in the same way at the same time, the probability of such a thing happening without two black hole mergers without a black hole, this binary black hole merger taking place somewhere in the universe was 1 in, I think, more than 65,000 years. So it was an extremely low probability event that this was not coming from the an astrophysical source, and hence this was the considered the detection of gravitational waves. Thousands of people worked, more than 1,000 people at least worked on this discovery, and three of the leaders, Rainer Weiss, Barry Barish, and Kip Thorne, were given the Nobel Prize in Physics in 2017. And so this is the collaboration, and as you can see, Indian researchers played a significant role in these detections, starting from the modeling the signal, which is necessary to detect the signal. The first part, when the binaries are going around, the in-spiral part, which required something called the post-Newtonian approximation, which was done in India. The last part, the ring down part, was also done by C.V. Vishweswara in 1970s. And the algorithm to detect this signal in noisy data, the whole mathematical foundation, a significant part of it was done also at IUCAA. All these things, of course, other countries also contributed, but the primary contribution came from India. And now we are also contributing significantly to experimental part as well, and also the detector characterization part, which is basically means that for every source that is detected, there are millions of instrumental artifacts which are present in the data, and to identify them and remove them. So these are the things. Anyway, now we'll start from the basics of little bit of general relativity and gravitational waves. Of course, general relativity takes a full semester course, so we cannot really cover the whole thing here, but I will tell you the most important taglines, let's say. So as you know, Newton's law of gravitation combined with Newton's laws of motion gives us a pretty good picture of the universe. That is how the planets are going around the sun, and all these motions of different things to a very high precision. We can predict when we are going to see a comet. We can predict when an eclipse is going to happen with a very, very high precision and things like that. And that is because of this, of our understanding of gravitation. And also we can say how exactly something is going to fall on the Earth. All these are governed by Newton's laws of gravitation and Newton's laws of motion. However, there was a fundamental problem with Newton's laws of gravitation, law of gravitation. That is the standard expression for force. If there are two objects, m1 and m2, and they are separated by a distance d, the force law reads g, where g is the constant of universal constant of gravitation, times m1 m2 by I said r or d, whatever, square, distance square. Now the problem in this formula is that there is no time involved. That is, if you do something to one of these masses, let's say there were collections of particle and antiparticle, and suddenly some door opens and they combine to form photons which have no rest mass, then the other mass immediately comes to know that there has been a change in m1. Now that violates the principle of relativity, that no information should travel at a speed more than the velocity of light in vacuum. So this is the fundamental thing about a relativistic theory, that the information propagation should have a finite speed. Nothing, you cannot break causality and so on. So Einstein was trying to formulate a theory which would incorporate this. And what Einstein found was that and it was of course a great theory, and it's very beautiful, that gravitation could be explained by geometry, and that is basically related to the fact to essentially Galileo's experiment, which showed that any object moves in an identical way in a gravitational field, of course, if there is no friction, etc., irrespective of their mass and what they are made of. If they become too massive, then of course they are going to start influencing the other object. But if their test masses, sort of, let's say, two balls, one iron ball and other one, let's say, even a thermocol ball, if they're in vacuum, they will fall with the same acceleration, and they will basically follow the same kind of motion. So this means that the motion of test particles, test masses under gravitational field is independent of their properties, and that also happens, I think you are familiar with this, in geometrical optics, for example, that when you do these lens diagrams, you don't have anything like what is the intensity of that light beam. Color is sometimes important when there is chromatic aberration, but generally those lens equations, if you remember, lens diagrams did not have any other property of light. In fact, they're kind of universal. So in this situation, of course, it is very likely that geometry can describe, and that was the basis of general theory of relativity. And then there is a whole theory. In Wheeler's word, I will finish this in one line essentially, that space-time tells matter how to move, and matter tells space-time how to curve. So it is basically like this, and it gets complicated because of this reason that so you know this analogy of a stretched rubber sheet, and you put a massive object there, and it sort of creates a curved geometry out of this flat sheet. And now if you take a test mass, let's say small ball bearing, and you roll it, the motion of that object actually depends on this geometry of this stretched sheet. Now, why? So this is a very well-known thing, and you must have seen it somewhere. Why it gets complicated is when if you instead of this one very heavy object and one very small object like a test mass, if you take two similarly massive objects and then start rolling it, then what happens is that one mass, let's say M1, starts influencing the curvature, which M2 is following, and then M2's motion becomes dependent on M1's motion, because of which the curvature changes that are introduced on this sheet by M2 also becomes dependent on M2's motion, and hence M1's motion. So in some sense, M1 starts influencing on its own motion through M2. So basically this gets non-linear, and they are kind of coupled, and then it becomes very difficult to solve them analytically, especially when they're close, because this motion becomes really coupled. When they're far away, and this perturbation, this curvature change is very small, then one can still manage it with analytically, which is what I said, that in-spiral part, and a lot of work was done in India. But then for the part when they are really going around and coming close, you need to solve it numerically. And there is basically a whole field to do that called numerical relativity. Okay, so I will show a little bit about this later on. Now, the thing is that general relativity predicts exotic objects like black holes, and you know about black holes. there must have been some discussion there. So I will not get into black holes specifically, except that there is an event horizon from which no other information can come out, including light. And also general relativity predicts gravitational waves. So Einstein predicted gravitational waves 100 years ago, more than 100 years ago, in 1916. However, he as far as I know from literature, he did not believe that it will be detected at any point. And that is the same reason why it took 100 years to detect it, because it required technological revolution to really detect these waves, because they produce very small perturbation. We'll come to that. Okay, this is not to scare you, but just to give you an idea of what I just said, that this equation is called Einstein's equation. You can add a lambda term, etc., that dark energy term also here, but let's consider this. The left-hand side represents the geometry of space-time. The right-hand side is energy momentum tensor. It represents the properties of matter, energy, mass energy. And these two are equal, I mean proportional. So and that is quite a remarkable equation. Now the thing is that, and it so far all the tests that have been done have passed this equation. So so far no test could be performed that has that this equation failed to explain. Now this is what is pretty complicated to solve in general, but then in the low gravitation limit, you can go to linearized gravity and sort, and then basically write the metric which determines the distance between 2 points. Like for example, in your in spherical polar coordinates, the distance between 2 points is given by dr square plus sine square theta, no, plus r square d theta square plus r square sine square theta d phi square. So you can write this matrix that which has the, or which is on diagonal in this particular case, and the components are 1 r square and r square sine square theta. So this matrix sort of is the metric for that coordinate system. But then it can get much more complicated and curved. And this is so in a situation when the metric is flat, you can always find a coordinate system where the diagonals can be made 1, and in fact for space time it becomes -1 1 1 1 or 1 -1 -1 -1, depending on which convention you follow. That is called the Minkowski metric. And then you can have a small perturbation h mu nu. And if you substitute this in this equation and use the right coordinate system, that is, choose the right gauge conditions, like what you do when you solve Maxwell's equation, for example, use something called Lorentz gauge and so on. So when you do that, then what you will get is an equation of this form. Okay, and this is again similar to the wave equation that you get in electrodynamics. Now, when the right hand side is 0, that is, if the wave is traveling in vacuum and it has been generated by some means, but then it is traveling in vacuum, then you can write this equation with only these two terms. See, this is space time, so there are 4 coordinates. The 0th coordinate is time, and then the other 3 are space coordinates. And you see this matrix has only 2 independent non-zero components, h plus and h cross, and these are the 2 polarizations of gravitational waves. And otherwise, this equation shows you that it is a propagating wave, and the velocity of this wave is c, the velocity of light. Okay, so there are some properties. I already said that these are the properties of gravitational waves. These are transverse waves, like electromagnetic waves. They travel at the speed of light, have 2 polarization states. They interact very weakly with matter, and that is a very important thing to understand. So since they interact very weakly with matter, they can travel long distances without getting distorted, unlike electromagnetic waves, which get attenuated because of absorption and so on. But then it also makes it very difficult to detect these waves. The advantage of this situation is that we can build more and more sensitive equipments to at some point detect those weak gravitational waves. That is much better, and that is possible. But what would be impossible is to clean up the dust in the universe and so on, which otherwise would have attenuated it. And because of this same reason, we can hope to see this gravitational waves from regions which are very dense, and light cannot often come out of that. Okay, so anyway, the thing is that a huge worldwide effort is on to develop gravitational wave astronomy, and basically which requires building more and more sensitive detectors to detect these waves from places from which normal electromagnetic radiation would not come. For example, when two black holes merge, of course, by definition, black holes don't emit anything. So these are some comparison which will sort of give you some idea about what are these. So for both electromagnetic waves and gravitational waves travel in vacuum. They don't need any medium. Okay, there are some questions. I'll answer them very quickly. So the source for electromagnetic waves, when we talk about generally, are incoherent superposition of atoms and molecules. It is like a light bulb. You know, there are many atoms which are emitting those electrons, but they're incoherent. Only for lasers it is coherent. But when we are talking about astronomical sources, of course, they are incoherent superposition. But when we talk about gravitational waves, so far what has been detected, it is not in general true. We are talking about two objects which are going around each other and emitting something. So this is a coherent emission. And hence we can actually measure the amplitude and phase of the wave, which we cannot do when, for example, we are looking at a star. The wavelengths also, what we talk about generally in electromagnetic waves, they exist in every frequency, but generally we talk about much smaller wavelength than gravitational waves. And then, as I said about the interaction, that they interact very weakly, gravitational waves interact very weakly, and it is the frequency also is kind of related to the resolution. But since the frequency is much higher for gravitational waves, as for electromagnetic waves, the resolution that we talk about is much smaller. So you can have a very small antenna to look at them. For gravitational waves, the resolution is much poor because we are talking about much lower frequency. It is like this lambda by Dirac criteria sort of thing. You need large detectors. So this part also I have already covered. Now, because the resolution is small, you can have small telescope for electromagnetic astronomy. You can use small telescopes and point it in different directions. For gravitational waves, the detectors are more like dipole antennas. You cannot really point them to any place, but these detectors keep detecting signals from different parts of the universe. Of course, so far we have not encountered a situation when two sources came simultaneously. But then if you have multiple detectors, by correlating them, you can get a much higher resolution, like what is done in radio astronomy, these GMRT antennas too. Okay, the questions are that, are polarization states of gravitational waves similar to electromagnetic waves? Well, almost similar, but then these are tensor waves. And the thing is that the polarization is at an angle of 45 degrees rather than 90 degrees. So for electromagnetic waves, this is the polarization, like one this way, one that way, but here it is 45 degrees. So this is one of the differences. And okay, next question is, how can gravitational waves, these waves interact weakly with matter when they are meant to interact with matter itself? Well, that does not, that they are interact with, I mean, these two sentences do not contradict, right? I mean, they can interact, but they can always interact weakly. How are we? So this is basically because the constant of, it's a universal constant of gravitation, G, is very small. Okay. How are we sure that gravitational waves also propagate with the speed of light? Well, it is a prediction. It comes from the equation I showed here. This equation, when you solve, actually it is already there in this box operator. It is 1 by c squared del square del t square minus nabla square, if you know what I mean. So that, because the t term, that del square del t square term has 1 by c square, that c, and the c is the velocity of light, that actually fixes the velocity of wave. So and that c comes right from the metric. Actually, I mean, if you, when you write the metric, that ds square equal to c square dt square minus dx square minus dy square minus dz square. I mean, at some point, if you have not studied, you will see this, at least in your special relativity course and so on. So then you will know that, but essentially from there, slowly it comes. And with equivalence principle, and with the idea that at every point in space and time, you can have a locally inertial frame where special relativity is valid. These things put together will give you that, but I cannot get into that right now. Okay. Okay, so this is the, okay, there is no other question right now. Okay, so this is the most promising source for gravitational waves, and as you know, we have only detected this source so far, about 50 of them. This is the compact binary coalescence, and I kind of already described to you when I was giving these two masses going on this stretched sheet example. What happens is that when they are going around each other, they emit gravitational waves. Because of that, they lose energy, they come a bit closer. As they come close, their frequency goes up. That period goes down. It is like inner planets have smaller period. And then they start moving at an even faster rate. So the quadrupole of this system starts changing at a faster rate, which is why they start losing energy at an even faster rate. More gravitational waves emit, and the frequency increases. So this is like an avalanche process, that when they start coming closer, they start coming closer at an even faster rate, and in the end, the last second becomes extremely violent and a huge amount of energy is emitted. So you can see here from this schematic that, you know, the wavelength is slowly reducing, that is, frequency is increasing. This part is really messy. This is solved by numerical relativity in supercomputer, and this is the merger phase. And then there is a ring down phase. It is a damped harmonic oscillation. Now I have a simulation to show you. Hope you can see it. So you can see that they're moving at very slowly at a lower frequency, and slowly the frequency is going to increase, and this amplitude of the wave is also going to increase. See, in the bottom, the amplitude is increasing, and then in the end, it will become extremely violent and messy, not so clean, and then it rings down. Yeah, that is typically what happens with binary merger. The thing is that if you substitute sort of typical values, you will see this number 10 to the minus 22. This is basically the strain that is produced by gravitational waves, and we will come to that. What the strain means, delta L by L, that is produced by gravitational waves. We will come to that shortly. The thing is that there are many other sources of gravitational waves, and we have only detected these compact binary coalescences, CBCs. And there are many predicted sources, supernova, gamma ray burst is of course connected to this, but there could be other ones. Then there are continuous sources, that is, things which are spinning with some deformity. If a sphere spins, it is not going to emit any gravitational waves. The sphere has to have some deformity, like a small hill and things like that. Then it can emit continuous gravitational waves, like a pulsar, like a sinusoidal-like wave. Okay, and there are many other sources like let's go to, yeah, supermassive black hole binaries. So these binaries, when they're going around, they can emit gravitational waves. Then there are stochastic sources. These sources could be collection of all these sources, meaning in a cluster of galaxy, let's say, there are many binaries happening, many binary mergers are happening, or many binaries are there, and they can create some kind of brightness. Okay, and you don't know which binary is emitting when or merging when, but overall there is a bright spot, just like what happens to an electric bulb. So that is meaning in electric bulb you don't know which atom emitted signals when, but it is that stochastic signal. And then of course there is this early universe metric perturbations which are still here and it may be observed at some point. I will talk about it in a short while. Okay, so there is a hand up by, let me see who is the person, Naren. Okay, go ahead and ask. Okay, so you don't have a question. Okay, let me see. Okay, that's fine. So normal matter does not create gravity. No, normal matter does create gravitational waves. There is this question. No, it's no problem, Naren. So okay, the thing is that any massive particle can create gravitational waves. Just that the amplitude will be extremely small. For example, when I'm doing this, I'm actually generating gravitational waves, but it will be extremely small. But what I mean is that if there is a sphere and the sphere is spinning, it is not going to generate any gravitational waves because the quadrupole moment has to change in order to generate gravitational waves. So it has to be some sense asymmetric motion. So this is the quadrupole formula. Basically, you see that this is the mass quadrupole moment, and it is kind of like a retarded potential sort of thing. So the second derivative of this quantity determines the gravitational waves. It falls as 1 by r distance. And this g by c to the power 4 is what makes this quantity these waves extremely small. Yeah, okay. And that is the kind of strain you expect in matter. I mean, this is another way of saying it, that the strain is proportional to the non-spherical part of the kinetic energy. That is an asymmetric part of the energy. Okay. So basically the point of what I wanted to say is that the gravitational wave sources span an enormous frequency range, and they are of different kinds. We have only seen some of the sources here. Okay, that is neutron star and black hole mergers or coalescences. There are many other sources like supernova, core collapse, different kinds of massive binaries. The thing is that when the mass is more, they become bigger. Black hole's mass is proportional to radius, unlike other normal objects. So when they go around, they touch at some point. And the thing is that this frequency is less when they are more massive. So in order to see supermassive black holes, you have to go to much lower frequencies in millihertz. Okay. Okay, there is a question. So we can say that even the fastest rotating pulsars would not cause G waves due to their rotation if the pulsars do not have any asymmetry. The pulsars can have some asymmetries. It is hard to believe for me that these objects are so symmetric. That is, if a pulsar is asymmetric, that is so there is a quantity which is defined as I, where I is the moment of inertia, IYY minus IXX by IZZ, where Z is the spin axis. If this quantity is 1 part in a million, then also there will be detectable gravitational waves. If it is smoother than that, then there will be no gravitational waves. Often these pulsars are fed by other cloud or star which is falling on that, so there can be some asymmetry. Then there is magnetic field, which the magnetic field energy can also be very strong and asymmetric inside a pulsar, and then they can become what are called magnetars. So there is a possibility of detection of gravitational waves from rotating pulsars, but so far we have not detected anything. We have only put upper limits. We are constraining and saying that they are smoother than, they are more symmetric than this value and so on. Okay, the next question is, how do neutron stars like pulsars have asymmetries? They may not have asymmetries. That is also possible, but they can, because there is matter falling often, from another star on them. So there can be, and it does not have to be absolutely symmetric also, right? Earth, for example, if you look at the Earth, it is not perfectly symmetric. There are some asymmetries. The Sun is slightly asymmetric. I mean, there you can see sunspots, etc. And we are talking about 1 part in a million asymmetry. So certainly that can be there. But we don't know whether they are asymmetric or not. That is why we are doing this astronomy. Will the intensity of gravitational vary with the extent of? Yes, more asymmetric it is. Given the same motion, if it is more asymmetric, it will generate more gravitational waves. That is for sure. Suppose a neutron star is spinning at a certain frequency, let's say millisecond pulsar, spinning at, let's say, a few hundred hertz, and then if two of them have the same frequency, but one has a slightly larger sort of like a lump than the other one, then the one which has more higher lump will emit gravitational waves at a faster, more gravitational waves. The amplitude will be more, frequency will be the same. Okay, so now I come to the detection part. The first indirect detection happened with the observation of a binary pulsar. So what happens is that as they go around, they emit gravitational waves, so the frequency changes, and also they start precessing slightly. Okay, meaning the orbits don't what is that called? Periapsis, right? That does not happen exactly at the same point. Start as precessing, and periastron. Yeah. So this thing, meaning the closest approach, time shifts, and this was monitored for a long time, for actually 30 years, for this pulsar, binary pulsar. I forgot the name. It's a Hull-Stellar binary pulsar, sometimes called. And these dots show the measurements, and the solid line is the prediction from general relativity. And you can see it's very clearly, it matches so wonderfully well. So this basically says that this system is indeed emitting gravitational waves, but it was an indirect detection because we did not detect the gravitational waves. How the energy is lost, that is what this signifies. And Hulse and Taylor got a Nobel Prize in, I forgot which year, 1992 maybe or something. Yeah. So, but this whole observation was taken for a long time, 30 years. Okay. Now I will come to the direct detection. Okay. Before that, there is a question. So again, if Betelgeuse goes to supernova, now if the supernova was extremely symmetric, we may not get any gravitational waves, but it is so unlikely that because Betelgeuse is so close that if there is a supernova, even a very small asymmetry will create enough gravitational waves that we should be able to see it. It will be quite a remarkable observation either way. Even if we don't detect any gravitational waves, supernovas will have to be so symmetric that it will be probably more exciting than if gravitational waves were detected. Okay, so the next question is, like photons of starting universe, where the G waves same detected, or is there a process? So I will come to this in the end. Of course, this will be one of the most interesting thing to detect, but we are far away from that so far right now. The future will start. I believe the future will see one of those detections or a non-detection, which will say something about the early universe. Okay, so first let us get into how to detect gravitational waves directly. So if there is a ring of particles and gravitational waves fall on that, then they execute this kind of motion. So if you have a rod here, then the rod would basically fluctuate, oscillate, and from there you could measure gravitational waves. But a better method is if you place two mirrors on this ring. I mean, there is no actual ring, but anyway, and then there is a beam splitter, and you create a Michelson interferometer. The motion creates this kind of oscillatory motion. So Michelson interferometers are good to find the arm length difference, and since one arm becomes shorter when the other is longer, this is ideal to measure it here, and there are other technical reasons. So Michelson interferometer is a better method. Okay. Now the thing is that these are the first attempts. This is Joe Weber with his bar. This is basically using this bar detector. Like when gravitational waves fall, the bar starts oscillating. It's a resonant bar. So it is, in order to get the signal, amplify the signal, if it is resonant and has a very high quality factor, near the resonance, the amplitude will be much more, but then that also reduces the bandwidth. So this becomes very narrow band, and also these detectors can only see from a certain directions of the sky. So this, even though this is extremely important step, because these are the detectors, this is the first step for meaning first step in the sense when people even started thinking about gravitational detection. So it's a very important step. But then this really could not detect anything, and there are but other attempts to improve the sensitivity of these detectors and then cool it cryogenically so that the Brownian motion reduces and so on. But so far, these detectors' sensitivity are quite limited. Okay, I'll just come to this question. First, let me explain how the gravitational waves are detected with this interferometer. So there is a beam splitter, and then light goes to this side and comes back, and then it gets combined, and then it gets collected here. Okay, and then the thing is that when gravitational wave falls, this arm length changes, which changes the interference pattern here, like and then by observing this intensity here in the photodetector, you would be able to say whether there is a gravitational wave or not. Actually, this instrument does not work exactly this way. I mean, there is no change in the here effectively. It is held at a certain frozen condition, and it's a feedback signal which is actually recorded, and that is the tells us what is the gravitational wave signal. So the question is that the entire space expands and contracts like this, won't the light also scale up and down accordingly? So why we will see any interference? Well, it has been shown mathematically that is not the case, and also the gravitational wave, the frequency of the light is much larger, which is huge. So the wavelength is very small. So what happens is that light makes several trips here before the gravitational wave signal has passed. So what happens is that the changes here happens much more slowly because of gravitational waves. Okay, so when you put together all these things, I mean, there is no so this instrument, Michelson interferometer, measures the path length. It keeps measuring the path length which is observed here, and as the gravitational waves pass, basically normally, this intensity changes slowly. That's what happens. But yes, this is a confusing thing to explain. But there are, you can find a full document, I think, written by Peter Solson, so specifically on explaining this. Okay. Now there are multiple detectors. So the two detectors, okay, there are multiple detectors which are operating. So there are two detectors in the US at Hanford and Livingston, which detected the first signal. Now there is a Virgo detector in Italy, which is also gaining sensitivity quite a bit. And so this three detector network is highly sensitive right now. There is a geo detector, it's a 600 meter detector, which is very important. It is there for a long time, and it is very important because a lot of the technologies that are used in LIGO are actually developed in this geo detector. Now, another detector which has just come up but has not reached significant sensitivity yet is the Kagura detector in Japan, which is an underground detector, and it uses cryogenic. It's different, uses a slightly different technology, and it has started taking data, but it will take some time to reach the sensitivity. And then there is the LIGO India detector, which is going to come up. The good thing about LIGO India is that when it comes online, let's say in 5-6 years, it is going to be using the same technology as the two other LIGO detectors. So the chances are pretty high that this detector can have even more sensitivity than the other detectors, like the Virgo and Kagura detectors, meaning it can be at the same level as the other two LIGO detectors. Okay, somebody has posted this link. Let me just check whether this is the same document I was talking about. Yeah, so I don't know this one or not. There is another document which is basically okay. If I find it, I can tell you which one it is. So that document addresses the question which was asked, that whether the change in light wave will due to gravitational waves will spoil the interference pattern. Okay, now this is the Hanford detector. It's 4 kilometers long. The reason we want a long detector is because the gravitational wave signal creates strain, so which is delta L by L. So longer the L, larger the delta L. So if you but then even then, a 4 kilometer is not enough, because the total so when the first detection happened, the fluctuation that was created in this arm because of gravitational waves was smaller than the size of a proton. So as you can imagine, that is a very small fluctuation. So we have to multiply it, amplify it. So the question here is that what kind of light is used in the interferometer? This is basically a laser light, which is a 1064 nanometer wavelength. Yeah, I will show you some of the pictures. So how to increase the light travel path? Well, you can fold the path. That is, it goes multiple times, but then this will require much bigger mirrors, and then there are issues which are technically challenging. So what is actually used is a Fabry-Perot cavities in each arms. That is, light goes inside this partially reflective mirror and then sort of gets trapped for a while before coming out, and effectively this kind of effectively increases the length of the interferometer, so that the gravity of signal is amplified. Okay, and this is the actual picture of what is there. I will not get into the whole complication, but there is a video lecture by Sendil Raja on the LIGO India YouTube channel. There is a GW at Home series. There is one lecture. You can go to that to know more details about the interferometer design. So basically, you can see that the power is amplified inside the Fabry-Perot cavity, and it can reach nearly a megawatt. That is a hell lot of power, and so that is one thing, and that could actually distort the mirror. And there are other lasers which are used to retain its shape. Now there is one more mirror which is put here, so that there is another resonant cavity which is created, which is called the power recycling mirror, and so it makes the this system pretty complicated. And then you can learn more about this. But all these things are done to increase the sensitivity. Okay. So these are some of the details which you can, which may be useful. That the length is like 4 kilometer. The wavelength that is used, somebody asked, it's 1064 nanometer. The power we have reached about 50 watt. So this, but then we can go up to 125 watt. That is the initial power, but then it gets amplified. The test mass is made of few silica and so on. And then all these things are going to change very soon. I mean, meaning within few years, because the detector will be upgraded. We want heavier mirror, because the light itself creates disturbance in the mirror, because there is radiation pressure. In order to reduce, the pressure is going to remain the same if you increase the laser power, and it is going to increase, in fact. But if you use a heavier mirror, that is going to go down. So similar things for all the non-gravitational forces. If you use heavier mirror, the motion will be less, and that is kind of obvious. But it is of course challenging to make heavier and heavier mirror and suspend them in a way that that is feasible. I'll tell you probably one thing about that. So this is basically sort of the noise budget, okay, meaning how much noise comes from in which frequency and what is the dominant component. So the lower frequencies are dominated by seismic noise created on the Earth. The higher frequencies are dominated by photon shot noise. That is when you increase the laser power, this noise can go down, but then the radiation pressure noise will go up. And then the central part is dominated by thermal noise. That is sort of like if you operate at room temperature, the vibrations of the molecules will affect the sensitivity of the detector. Okay, so I have quite a bit of things to cover still. So let me see what are the things that I should cover. Okay. Okay, so anyway, so this is the basic picture of how it looks like. These are these vacuum tubes. This is 4 kilometer. This is where the beam splitter sits. This is the one mirror of the Febrile cavities, the other the end mirror, and so on. So I'll slowly, quickly go through these pictures, so you can see this is how big the tube is compared to people. This is like a few feet vacuum tube, and then this is the mirror. The mirror is suspended by multiple suspensions. So basically, every pendulum works like a frequency isolator. I mean, if you take a pendulum and then start rotating slowly, you will see that it will moving with your hand. But if you start moving it extremely fast on the top, it does not move. It does not move much. So the pendulum is like a high frequency, a low pass filter. So if you so it absorbs, it blocks noise at higher frequencies, which is what we want. So if you have multiple stages, then it blocks even more. And basically, the noise above 10 hertz could be blocked this way. But the lower frequencies are not possible to block, and that is why people have to go to space for low frequency detections. In order to reduce the thermal noise, these mirrors are actually, even though these are 40 kilo, they are actually hung with the same material, that is fused silica, almost like glass. Basically, these glass mirrors, very expensive ones, are hanging by glass threads. Okay, and this is the laser. There's for advanced LIGO, and this is the optics. Sort of, there are a lot of things involved in the optics, cleaning the unwanted mode, then making the laser frequency very stable, and all sorts of things. And finally, you get this kind of curve. So even though the sensitivity curves, which is designed, is much smoother, actual curves look far more complicated, and all the noise is not yet properly understood. But as you can, one thing to notice is that lower it is the better, because then you can detect even finer signals. So the whole game is to reduce the noise. Okay, so even with all this, the noise is quite dominating, and then we need to use innovative data analysis techniques to extract the signal. So what is used is called matched filtering. It is like, I'll show you very quickly with an animation. So suppose there is a signal embedded here, this red one. Okay, but you know the shape of the signal, but you don't know where it is. So what you will do, you will place the signal here and correlate with the data, and then plot the correlation, and then move the signal again and correlate, and then you will get something like this. But when the signal matches this hidden signal, you get a peak. So this animation, it is nothing is moving, it is just plotting here, and see when they match, there is a high peak. And from this you can say that, oh, there may be the same pattern is hidden there in the data. Now with all this, the thing is that when we had the initial LIGO detector, it was basically a technology demonstrator, and the rate that we could expect was 0.02 per year, which means that there was a 2% probability of detection of a signal. But with advanced LIGO, that increased very significantly, and now we know that there are almost a detection per week. And now you see here something interesting, that the prediction was that we will have 40 neutron star merger, 10 neutron star black hole merger, and 20 black hole mergers every year. We already have detected about 50 black hole mergers, but we have detected only 1 or 2 neutron star merger. So see how observation completely changes the theoretical understanding. This plot these numbers sort of show that there are far too many heavy black holes than we expected. So the reason why we could not see earlier so many with the initial LIGO was because the horizon was small. And now with advanced LIGO, the horizon has increased by a factor of 10 almost. Still the full sensitivity has not been reached. But that means the area, the volume that is covered went up by more than a factor of 1,000. And that is why the rates become so much. So which is why when the instrument is sensitivity could be, if the sensitivity could be improved by factor of 2-3, that's a big deal, because it increases the detection rate by a factor of 10. Okay, so there are many things which were done in advanced LIGO, like increasing laser power, etc. The mass was increased from 10 kg to I think 10 kg to 40 kg. All those things were happened. But let me go to so this I'll just keep. Okay, so after all this, finally gravitational waves were detected even before the full target sensitivity was reached. And that is understandable, because when the target sensitivity is reached, there is a detection every week. But even before that, when the detector was even operating in the engineering mode, it started detecting. And in 3 months of operation, it detected 3 signals, so like once a month sort of thing. The interesting part in this simulation was that it is sort of a realistic simulation, and you might have seen similar simulations done by shown in this movie called Interstellar, not for gravitational waves, but this lensing by black holes. The next big event that happened was this binary neutron star detection, the GW170817, where which was since it was a binary neutron star merger, it emitted electromagnetic waves also. Black holes, of course, don't emit anything else. And then it could be followed up by in gamma rays, then optical, infrared, I'm not sure about infrared, optical, radio, and all those different frequencies. And they told us many different things. So how was it localized? So, okay, I'll show you this video. The thing is that initially, this is the Fermi gamma ray error circle. It's very big. Then there was another one. Still, it is pretty big. Then comes LIGO-Virgo. Now, important thing is that with LIGO and Virgo, you will see that error reduces quite dramatically. With 2 detectors, it would not. With LIGO, 2 LIGO and Virgo, it reduced. Even the Virgo did not detect anything. See, this is pretty big. This is small. Non-detection can also help you in localizing, because as long as the detector is sensitive, because if it was in the sensitive zone, it would have detected it. And from there, people could locate the host galaxy and then we could get the redshift of the galaxy, and that told us, the Hubble constant. Okay, so in this task, a large number of telescopes operated day and night, and of course, telescopes, electromagnetic telescopes, except for radio ones, can only operate in the daytime, in the night time. So you need a global coverage, and 3 Indian detectors, Astro, GMRT, Himalayan Chandra telescope, they also participated in this. Okay, so what did we learn from this? First, let's see this video. So this shows that initially there is a prompt emission, and then this is the afterglow when this jet hits the medium outside. These things were all theoretically proposed, but this is the first time it was actually observed, and the proper connection between gamma ray burst and binary neutron star merger could be established. Then there was this very interesting thing. So the signal that was observed in Fermi, this is the sound of gravitational wave. If you converted it, the wave to a audio frequency wave. The gamma ray burst was observed 2 seconds later. So essentially almost at the same time. The total path light traveled to after the merger and before it is detected is something of the order of 10 to the 15 light seconds, 10 to the 15 to 10 to the 16 light seconds. So actually few times 10 to the 15 light seconds. So which means, and then there was only 2 seconds delay between these two signals, which means that velocity of light and velocity of gravitational waves must be similar to the accuracy of 10 to few parts in 10 to the 16. So that you can see that this is for all practical purposes, you can say they are basically the same, even though people will still see if there is any difference. This is assuming that the electromagnetic waves and gravitational waves started almost at the same time. Okay, now let us move on. So what else did we know? So you know that there is always a question that where did these heavy elements in the periodic table, which you see, come from? Because you can always take lighter elements and then fuse them to form a bigger element. And the fission part, that is, you can break down uranium into smaller elements happen when you induce it. But in the universe, how would you create these heavy elements? Because generally you always try to go towards iron. So supernovas could not explain the whole composition that we see, and it was predicted that probably during these binary neutron star mergers they are created, and this was also observationally verified by the after the GW17 OH17 observation, using all these kilonova observations and so on. Okay, so basically many things we learned, that there is a binary neutron star merger and gamma ray burst connection. Now, and then I said there's how the heavy elements are created in the universe, those things. But one more interesting thing that we learned, because so you see we had a different estimate of Hubble constant. So this is, you cannot see it properly probably, but this is basically Hubble constant on the x-axis, and this is, let's say, some probability. Now this green and this orangish color, they essentially show the measurements from CMB and supernova. You see that they're very precise measurements. However, they don't match. So they are not overlapping, which means that one of them must be wrong, or both. Now we have, with gravitational waves, we got this huge error bar with this observation, because we could locate the host galaxy, we could get its redshift, and then from the gravitational wave observation, we could get its distance, so we can get Hubble constant. But then, since we can stack up, that is, we can add more and more observations, and this can become narrower and narrower, hopefully one day we will be able to distinguish these two. This is basically the same thing shown by in Planck's plot, Planck CMB observations, CMB missions sort of graphic, which shows how the Hubble constant measurements are becoming more and more accurate. And you can see there are accuracy, but they don't match. And then here is the LIGO measurement, LIGO-Virgo measurement, and when they become smaller, it should be able to distinguish between, say, which one of these is probably correct. This is where LIGO India can play a very important role. Okay. So anyway, there are many, actually this plot has got updated now. We have about 50 detections now. And already we see that there are some detections in this area where nobody detected anything, between, let's say, 2 to 5 solar masses. And we don't know what these objects are, because neutron stars, whatever have been detected, are 2 solar mass or less. Black holes are usually 5 or more. So this is I think 2.9 solar mass. So is it a neutron star or a black hole? We still don't know. Okay. Now, with all this, we are in the very beginning of gravitational wave astronomy. We have just started, and a lot of things have to be done. So now, first thing would be to build a network of detectors and follow up many sources with electromagnetic telescopes, which will be possible with LIGO India, and then build instruments at different frequencies, go to space, because we cannot yet see the supermassive black holes. And LIGO India is going to be most important for us. So now I will very quickly go through this, maybe in 5-10 minutes, if I have time, to tell you more about the future. The future is sort of connected to whatever I have presented, so it is not going to be exactly equal amount of time will be necessary, but I think I'll be able to wrap up in 10 minutes. The thing is that we have learned very little, even though we have detected 50 sources, we learned very little about this compact binary, how they are originated, how they evolve, and what is their population, how many black holes are there in the universe. All these questions are still quite unknown. So we have to, we can get quite a bit of handle on these questions with gravitational wave astronomy. Then cosmology also, as I said, I mean, you can get a better distance ladder. Then maybe we can get the signal that was generated in the very early universe, like inflation. Then we can do a lot of fundamental physics. So is Einstein's theory the ultimate theory? We can check that. There is something called the no-hair theorem for black holes, which sort of tells us that the final ring-out signal that we observe is completely determined by the mass and angular momentum of the final black hole, which can be derived from the initial to the mass and orbital angular momentum of the system. Now the question is that but in order to test this, we need very high sensitivity at those for the ring down part, which is right now not enough. We need much more sensitive detectors. Now every theory breaks down at some point. So far, that is what we have seen, like, for example, Newton's laws, etc. So we have to see whether Einstein's theory breaks down at some limit. Maybe in the strong field, we need some corrections to Einstein's theory. Those things we have to test. Then there are other things like the dark energy equation of state. If we can get a precise measurement of the evolution of the Hubble constant with redshift, maybe we will be able to do that. That is how the rate of expansion of the universe is changing with distance. That is when we are looking at the past. Then there is the neutron star equation of days. Neutron stars are basically soup of neutrons. So hopefully with more and more observations, we will have a handle on that. And all those things, science, this kind of science is remaining. So there is a lot to do. And also the surprises. Every field of astronomy has seen surprises which have completely changed the way we look at the universe. For example, pulsars, cosmic microwave background, expansion of the universe. All these things were kind of surprises. Okay, so there are this whole bunch of sources. I mean, in these frequency bands, you can see there are different kinds of sources which are predicted, and there are many detectors also which have been proposed. And this is the next few decades are going to be quite exciting with all this. You can look it up on the internet. So effectively, see, these are the maps of the sky which we have been made in electromagnetic waves. This is radio to gamma ray, and we want to make such maps, of course, also in gravitational waves. But right now we have only few detections here, few spots which are not persistent. So and as you can see, there is a very long way to go. We can sort of compare it like this. This is Galileo's telescope, which used this telescope to observe the, I think, Jupiter's moons and so on. So we are basically here right now. We have just started observing. And this also, observed, let's say, phases of Venus and things like that. And then in the next 400 years, electromagnetic astronomy reached here. These are some of the state-of-the-art instruments like the Keck telescopes, Hubble Space Telescope, GMRT, etc. So right now we are at this stage, and so you can imagine there's how much scope is there for the next few decades. Okay, so the thing is that the planning has to start, of course, right now, because all these instruments take decades to build, 20-30 years. So this was initial LIGO. The advanced LIGO, which have detected the sources, is like 10 times more. And there is a third generation detectors, which are called this is one of the designs, the European one. It's called the Einstein's telescope. And then there will be Cosmic Explorer and things like that. That is the American proposal, and this is what it is going to do. So you see that compared to these detectors, the Cosmic Explorer will have much more sensitivity. And if you look at this plot, this is with redshift, and you see that we are right now observing in this region, which is kind of empty. There is because how the distance changes with redshift, because the universe was much smaller at a higher redshift, a lot of things are happening in this region. Okay, so if we can reach this part, then we will see a large number of black hole and neutron star merger, and that is the aim. So this is the next. These are the next steps. I'll first tell you about the next steps, then briefly mention about LIGO India. So this is sort of how some tentative plan for Einstein telescope. It will be underground, 10-kilometer arms, and triangular shape, but then all this can change. These are tentative designs. Then there will be a space-based mission called LISA, which will probably fly in 2034. It will be 3 satellites which will be following the Earth like this, and they will exchange laser lights. They will have about 1,000,000-kilometer arm length. In space, of course, there is no seismic noise, but then there are other kinds of noises are there, and this will be able to see supermassive black holes. Then there are other proposals how to observe the gravitational waves which were generated during cosmic inflation, that is when the universe was less than a second old, and there are these proposals for. So this can be done probably by observing the polarization pattern of the cosmic microwave background, or maybe directly by sending an interferometer in space. One proposal is called DESIGO, Decihertz Interferometer Gravitational Wave Observatory. Okay, now coming back to the LIGO India part. So as I said, that if you have a network of detectors, we can actually locate the sources on the sky very well. And that is basically like if you imagine GPS satellites. If you have only 2, you can locate a source on a ring on the sky. But if you have 3, you can pinpoint it. And these are the sort of these are the radar circles which we saw with 2 detectors. And when Virgo detector was online with this binary neutron star detector, the area becomes much smaller. And if LIGO India was on when the first detection happened, again the area would have been much smaller. Now that why smaller area is important. It is because if the electromagnetic telescopes have to follow that scan this area on the sky, if it is too large, it will take very long time for them to scan, which means that the source might have fainted by then. So if it can be scanned very quickly, then there is a chance that we'll be able to know something. Like Hubble concept, it's very fundamental, right? I mean, how fast the universe is expanding, because that also tells us many other things about the universe. Now, why the LIGO India is important? Because when this is India, this is the Earth basically seen from the top. This is America and so on. These are the two LIGO detectors. See, the light travel time distance between them is only 10 milliseconds. With Virgo also it is 25, 26. When the Indian detector comes, it brings much longer baselines. It's like 36 and 39 milliseconds. So it's more than 10,000 kilometers. Okay, so this will have higher resolution. It is like this lambda by d sort of thing. This plot was made by one of the ex-IICAA Pune student to show that how the baselines increase when LIGO India comes online. You can see that, and the area of the triangle kind of increases much more when you include this Indian detector, and also the total integrated area increases. Okay, so here is another way to see it. So right now we can localize the sources in a very bad way. I mean, even though we could follow up, but you see that only in some regions of the sky the localization area is small. Most of the parts it is pretty bad. Okay, but with when the Indian detector is online, these areas become much smaller, and which will allow those fast follow-up of those electromagnetic sources. So right now the plan is that it will be located, so several sites were surveyed all over India, and it will be located in Maharashtra near Hingoli. The thing is that the LIGO India is a very highly multidisciplinary field, so it is not just for physicists or astronomers. People from various trades can take part, and this is one of the, and this provides an interesting platform for people to collaborate and hopefully get another mission, not necessarily on gravitational waves, but keep doing this kind of big science. So basically many of the institutions are involved already, and people collaborate to, in fact, my institute IUCAA sort of plays this role of bringing people from different institutes together to collaborate. And if some of you want to take part, then you can. There are ways you can come through your own institute, which happens to be IICAA Pune, and there are other places also. Okay, and also it requires quite a bit of computing power. We have host those things here. Now the thing is that I will end by saying that Galileo's success was because he introduced cutting-edge technology of his time in astronomy, and that's how he got all those. He could start the whole field of proper observational astronomy. It was there earlier, but then Galileo basically brought a renaissance. So for LIGO and these gravitational waves also, astronomy also, we are using the cutting edge technology, the laser technology, suspension, all those things. And also on the sort of semi-theoretical side, there is machine learning and all those things. And it can be used in many different ways. So the point is that many of you, like, who are thinking about doing career, not necessarily in gravitational waves, I think it is important to keep your eyes open to see what are the new technologies and use it for your research, and that probably makes research much more exciting also. Okay, so I think I stop here. This is just a brief summary that gravitational waves have been detected, starting a new era in astronomy. And new windows of astronomy not only just provide a better picture of the universe, it changes the way we understand the universe. As I said, with gravitational wave astronomy, just 5 years old, we already see that what we expected in terms of the number of black holes, etc., are completely different now. Now, the advanced and other future detectors are being made, and we need to make. It is not just the detectors are made, meaning you just get land and then start building something with the existing technology. The whole technology has to be taken forward in many ways. You need different analysis techniques, different signal, more precise signal models, everything that is numerical relativity. All those things have to progress together. Now, hope in the next few years we'll have the LIGO India detector. And I stop here. There are already many questions, and I will keep answering them. Okay, so there is one question here that what will be the arm cavity length for the upcoming LIGO India detector? It is going to be the same, 4 kilometers, like the LIGO detectors. We are going to use basically the same technology. Even though when LIGO India comes online, the technology that will be used in LIGO will also be different. It will be something called the A+ technology, and some of the Indian members will also take part in developing that technology. Along with the mass and angular momentum, does not charge remain conserved? Yeah, charge also, but I don't know whether really black holes will have charge or not. Yeah, but then it can depend on charge as well, if they are charged. Okay, any other questions? When? Well, hopefully in 2016. That is the plan. But because of COVID, etc., there will be a little bit of delay. How should one go about applying for a summer project or internship in IUCAA? For ISAR students, it has been pretty straightforward. Summer student is a bit more complicated because if you need accommodation and so on, then you have to apply for the usual regular IUCAA's summer program. But if you want to do a long-term final year project, that many students do here, so that is not a big problem. Of course, the person has to be available. I mean, whoever you want to do a project with has to be available and so on. Yeah.
Okay, so thank you, sir, for this wonderful talk. I'm sure a lot of people would have been excited about this field by this. So if anyone wants to ask questions, they can unmute and ask.
I think there were a lot of questions already on the chat box, and I answered them.
Yeah. Okay. Yeah, I had a question.
Okay, yeah, go ahead.
Yeah. So you had mentioned I think in the beginning that even a supernova explosion, asymmetric explosion could give out gravitational waves. But to me, I mean, how would you exactly even like model a supernova? I mean, how would you even understand if it's from a supernova, because it's just a brief explosion?
Correct, right. So the thing is that if it is a distant supernova, of course there are some patterns which have been proposed. It is I think it was a sine Gaussian type signal that will come from supernova. So there are some model that has been proposed, but my belief is that finding a distant supernova is going to be quite challenging, and saying that it is a supernova. However, whenever we are detecting a signal, a detection is really confirmed when it is detected in two detectors simultaneously, almost simultaneously. The maximum light travel time between two detectors is few milliseconds. Okay, well, tens of milliseconds. So millisecond is of course very small, right? I mean, it is the thing is that it is, so if it is, suppose you have two detectors and the signal, something happens exactly on the plane bisecting the line joining these two detectors, then it will be zero delay, okay, on the sky. Otherwise there will be a delay, but the maximum delay possible is for the two LIGO detectors is 10 milliseconds. So when in that span of time you see two signals of the same kind in two detectors, then you will be sure that this is an astrophysical event. Now, whether you will be able to confidently call it a supernova or not depends on the theoretical prediction. Like in the first detection, theoretical prediction was a chirp signal. I mean, this signal whose frequency and amplitude both are increasing with time. So then we could say that these are black hole mergers. For supernova, if you see a pattern like this, then maybe you can call it a supernova. But a bigger chance is that when you see a supernova is also seen electromagnetically. So if you see a signal in two detectors, or three detectors, which corresponds to the same direction where a supernova has been observed by electromagnetic telescope, then that would be a big confirmation that there is a supernova, and that can tell us about Hubble constant again.
Yes, so if it's localizable, then it would be much better.
Yeah, then we will be able to confirm that it was a supernova or not. Yeah.
Okay. There is a question in the chat.
Okay. How do we distinguish between astrophysical and terrestrial astrophysics? Okay. So the thing is that this is complicated thing, of course, messy business. There are certain signatures. The terrestrial signals are, so far we are detecting only the chirp signal, that is the signal from binaries. So that signal is very well known, that how it should look like. Anything else which creates a power flux, like a large amount of power in the detector, is most likely an instrumental glitch, okay, or artifact. So what is done is that a lot of machine learning techniques are being used right now. There are many other chi-square techniques which are used. So these things are done to distinguish between astrophysical and terrestrial events. Also, LIGOs. So the main signal is this path difference between the Michelson arms, and that is basically one channel. But LIGO actually has 200,000, that is 2 lakh, 1 lakh or 2 lakh, I forgot, channels, which records the measurements by different monitoring channels. So all these, so when a detection happens, basically people go through a large number of these monitoring channels to see whether there was any other glitches, environmental artifacts, which were noted in these detectors at the same time. And if something is found, then the data is flagged, saying that this is not usable data. Yeah.
I had another question.
Yeah, sure.
So I think in another slide you said about how the predictions about the neutron star and black hole mergers flipped.
Yeah.
So how exactly were they predicted initially, and is there any reason for why it turned out to be wrong?
Well, the thing is that it was predicted based on the knowledge of astronomy at that time. At that time, meaning only 5 years back, actually. That was, or not 5 years back, but less than 10 years back, as far as I remember, that paper was written. So, but people did not have much idea about black holes, because black holes are not seen otherwise, right? I mean, it was basically some X-ray observation told us some idea about a certain set of black holes. People are thinking that black holes would be mainly few solar masses. But the first detection already created a situation that we detected 36 and 29 solar mass black holes. That is already very big. People are not even looking for such big black holes. And now we have detected 150 solar mass black hole as well. So there is a lot of detection now. So essentially, that is how the observational astronomy completely changes the thing. 5 years back, or little more than that, meaning just before advanced LIGO started, the main question was that whether advanced LIGO will be able to detect anything. And now the question within 5 years have changed to how many we are going to detect and so on, and completely different things. So things change quite dramatically.
Right. And yeah, so there were more binary neutron star detections even after the 2017 one, right?
There is but then none of them.
Why weren't there any?
No follow up. Then also, two of them could be binary neutron star, but may not be binary neutron star. Could be meaning at least one. There could be one black hole, one binary neutron star, but it's not clear what they were finally. The advantage about but the numbers are still small. It could be a selection effect also. We did consider that when the full sensitivity of the detectors are reached, probably we will get many more binary neutron stars, because right now we are getting only the ones which are which produce a burst of the signal. So it's more probable to detect the black holes right now, but maybe binary neutron stars are much larger in population, they are present. But for all to conclude this, we will need many more observations, much more sensitive detectors. So
yeah, and 50 is a small number too.
50 is a very small number, and only 2 binary neutron stars. I mean, we need hundreds, then it will be good.
Right.
Yeah.
Thank you. Is there any more? Are there any more questions? Okay, I'll stop the recording. Yeah, I think it's all.